So, good afternoon everyone. Just curiosity. My computer yesterday decided to say good morning with a blue screen. So basically I had to format it and prepare presentation again. So if you find some mistake, I'm sorry. Please bear with me. So, as the title says, this was an investigation regarding laser powder bed fusion producing components, and we wanted to understand the influence of the direction of printing on the strength of these components, the effect post-heat treatment would have, and how these materials would respond to high strain rate deformation. So I'll go over the motivation for my work, the experimental methodology that we carried out, the results and some conclusions. And here on the side you have an example of one specimen that was produced and tested in a split Hopkinson bar apparatus at a strain rate of 300 per second. So the influence on components produced by additive manufacturing is of great interest now with the exploration of potential applications ever more in aerospace. Also begins to start the need for the knowledge on how these would react to impact, for example, and other type of deformations in environments like space applications or nautical applications, for example. And so it arises the need to understand how the material would behave and what could be done to mitigate this, either in the process or post-process, and the heat treatment and the direction of printing. So we wanted to know, to understand if the building direction and how the building direction would influence. We know that it has influence, of course, how the material settles in the end, and how a post-process heat treatment could or help or not, if it would be cost-effective, let's say, or if it would be reasonable to apply it, if the gain would be considerable or not. So basically, we tested the three building directions. And we used heat treatment after that for each of the three building directions in order to compare with not heat treated, and also we tested at quasi-static and at high strain rate and very thin specimens. This was the equipment that was used to produce the components from which the specimens were manufactured. Basically, just an overview of the setting, and this would be the specimen with a millimeter of thickness and let's say a micro-flat tensile specimen. In order to be, we would be able to test it and the split Hopkinson bar. So here is the pattern that we would use also in order to make the digital image correlation. In the quasi-static as a plus. In the case of the split Hopkinson bar is also to understand and to guarantee that we can achieve breakage of the material in the first impact of the wave. Because it happens that it doesn't split completely in the first impact, and not always it's detectable by the output of the signal that the wave gives. So here is the setup for quasi-static, which would be tested with the same setup as is used in the split Hopkinson bar. Nothing special. And here is the bar. For example, here it's an apparatus which has 4 bars, and 2 in compression and 2 in tension. And the bar to test this specimen was made of titanium. So I think, yes, this is a video that was recorded with a high-speed camera at 125,000 frames per second. And here you're seeing the 5 frames per second. So basically, if you can see here, this is literally a small fracture of paint floating around. And we, in this case, of course, it's metal, but we use it to test also composites, since it's also in focus now in additive manufacturing. And basically, we wanted to understand how this building direction would, if we could manage to see the difference in how the material would react at such a high strain rate, which, if you think about it, would minimize, even if the material at the quasi-static state testing demonstrates a lot of change in behavior at high speed, at high deformation rates, that reduces substantially. So we wanted to understand if we could still detect it, if it would be still affecting the behavior of the material. Here, just a normal for a normal sized specimen produced, we could see already the effect of which is expected, the effect of the heat-treated specimen versus the non-heat-treated specimen. These are already microflat tensile specimens. This one is the heat-treated specimen. We can see again the expected behavior, the influence of the expected behavior on the material. This was the vertical build direction. So basically, up from the powder bed surface. This would be the on the side, meaning the specimen would be produced on its side, so that the lines of deposition would be along the direction of the tests. We can see here that the effect is not it's not as clear as the previous section already. You can see that for the quasi-static testing, even the heat-treated specimen varied in the beginning, and not only the expected behavior from material science. Here is the horizontal building direction, which we will see that yielded the best performance. Here are the results from the high strain rate testing. You can see here that there's a lot of fluctuation in the signal at the beginning, especially because we are going very fast from no excitation to a very high deformation. So the material, it's very common that in the beginning of this test, the material such as additive manufacture, produced by additive manufacture, has this non-linear behavior because of the way the wave propagates through the material. So basically what happens, we are blasting a wave through the material, we are measuring the wave passing before it reaches the specimen, and then we measure the reflection and what goes through the material. So hence these variations given the intrinsic, let's say, structure of the material. Here is the vertical, so this is the vertical, and we can see that it achieved about 250. Here is the vertical plus heat treated. So we saw some change, but again, is much less pronounced than the quasi-static. For the on-site building direction, the fracture also varied slightly, and how the material responded to the initial, let's say, instantaneous phase of excitement was also different. The propagation was, let's say, smoother than in the case of the vertical building direction. Here was plus the heat treatment. You can see that there is a smoothness, a smoothing of the initial phase, but the overall end result it was very similar, so not a big effect here. The horizontal direction, it was where we found more, let's say, scatter of the results. This, of course, has to do with how the specimens are produced and how the wave is propagating along the direction of the material, and it can basically encounter the inner defects, let's say, on the material in a different way and propagate differently from, for example, here we would have a much more clear typical fracture. Instead, on the horizontal, we would already have some sort of, let's say, 45 degrees that the crack would try to make. Again, on the heat treatment, we would see a bit of smoothing on the initial behavior of the material, but okay, sorry. And just to finish the comparison with all the heat treatment, the quasi-static and the high strain rate. So basically, for the high strain rate, the three conditions of fabrication were very similar. But in the case of the quasi-static strain rate is where we would see the heat effect, the post-heat treatment effect, and the variations with the direction of build. And I conclude my presentation.
Thank you very much.
Are there questions from the audience?
Yeah. How do you measure the strain rate? For high strain rate, how you were measuring the strain rate, and what was the strain rate?
We were using the high-speed camera.
So digital image correlation.
Yes, we did a digital image correlation to.
So what was the strain rate? Like
300.
300. Okay.
Yes.
So I was just wondering.
It's a range. It's in.
Yeah, for sure.
But it's between 290 and 310.
So I was wondering, like the first peak you were talking about, maybe just inertia effect of the material. Because when you suddenly load, obviously the inertia effect,
Yes.
because you suddenly accelerate the sample. You know?
Exactly.
So in my opinion, I believe the first instantaneous peak is not a material behavior, rather than inertial effect.
But the propagation of the wave is so fast that...
Exactly, that's why the first wave is usually taken as inertia wave rather than material behavior indication.
But it has to be, the inertia will be correlated to the structure of the material, that how the wave propagates within the material.
No, not really. Inertia wave is like a structure property, not a material property.
Okay.
So you cannot say that it was like a strain rate sensitivity. No, in my opinion. But we can discuss later.
Okay.
Yeah, because
So
it
why
usually
would you-
comes in the noise, you know, the inertia effect is more noise.
Understood. But then what would you say the effect of the heat treatment would be on that? Because we saw the smoothing of the...
But it's very stochastic, so I cannot comment on the noise, you know, noise cannot be reproduced, so I don't know.
Yeah, we can talk later. Thank you.
In my opinion, another way to really look at the strain rate dependency of a material, you just do, let's say, simple tensile, where, or with the machine where you can vary the strain rate during the test. So you can really see the jump on the same material. Then you eliminate a lot of factors with different samples. So you are testing on the same sample with different strain, and then you can see jump or, you know, the...
But you would be able to do so, to go from quasi-static to such a high value?
I'm not sure how much higher, but it gives fair indication. Let's say I go from 10 to the power -6 to 10 to the power -1, and then you have 5 degrees of difference, 5 order of difference. And then if there is sensitivity to a strain, you will be really able to pick that.
In that
Yeah.
in that range.
Yeah, first all in that range, and that will give you clear indication, and then you can go for this kind of high deformation. Thank you.
We have time
Sorry?
just for Short question.
Which cameras you use for the AC?
Photon.
Very quick.
Thank you very much.
Thank you.